Okay, good. So we're going to graph this function, okay? It has x in the exponent. Everybody should be doing this right now. You should have out a piece of paper. This is your notes. Let's go. Okay? So you're graphing y equals 2 to the power of x. How do you put in the power of x? Yeah, they call it like a caret. Okay? The button that looks like that, and it is right below the clear button. Okay? And then you can type in whatever you want as the exponent, and that's how you'll type in x. So you'll go to your y equals. You'll type in 2 to the power of x. Then go ahead and put it in a standard window. And look at the graph. Okay. Now this says plug in points to the table below. We're going to use the table that your calculator can make for us. Okay. So how would you generally describe the shape of this curve? I don't know. What would you guys say is happening? What's that? Okay, it's curved. Sure. Okay, so it seems to have some positive correlation. So that kind of leads into these questions right here. Go to the table set on your calculator. So second window. And it's going to ask you what you want to set it at. Go ahead and set your table to start at 0 and count by ones. So you want the table start to be 0, and you want the delta table to be 1. The little triangle is a delta, okay? Science people, right? Always calculates change in things, okay? So delta is how you want your table to change by 1 unit. Okay, and then go ahead and go look at the table. So then go second and choose graph, which is the table button. All right, so first thing I want you to look at is what happens to y as x gets bigger. So scroll down your table, and as you see the x values increasing from 2 to 3 to 4 to 5 to 6, etc., what's happening to the y values? So as x is getting bigger, y is? Dana? Okay, it's like doubling every time, right? Getting bigger, double, and then double what the double was, and then double, right? Getting kind of crazy. Okay, so drastically starting to grow. And that's why you saw that curve drastically increase on your graph, like Monet described as a positive correlation. Okay? Now I want you to scroll back to 0. And then I want you to scroll along your table in the direction as x values get negative. Okay? So what happens to y as x goes from -1 to -2 to -3 to -4, and you scroll that direction? Julian? Okay, they're getting divided by 2. Okay? When will you reach 0? You guys can't find it in your table?
It just goes to, like, scientific notation.
Okay, it goes to scientific notation, so things like 0.000000 something. What's happening to this function? It's getting smaller, okay? But is it ever reaching 0? Oh, you can see where I'm going with this? Okay, so it's like, let's say I wanted to walk from here to the back wall, right? But I was going to do it by cutting my distance in half, kind of like how the function is cutting each thing in half, right? So physically, let's say that I'm like 20 feet from the wall. Then when I move my distance of half, so I cut my distance in half the first time, then I'm 10 feet from the wall or whatever. Okay, totally estimating, whatever. Then I cut my distance in half again, and then I'm 5 feet from the wall. Then I cut my distance in half again. Say I'm 2.5 feet from the wall. Then I cut my distance in half again, 1.25. Then I cut my distance in half again. I don't know, point something, right? And now I have physically run into the wall because I take up space, okay? A lot of it, all right? So I take up space, so therefore I physically cannot get closer to the wall. But mathematically, if I continued to cut my distance in half, could I continue to get closer to the wall? Would I technically ever reach the wall? Ooh, it is, right? So I would continue to get closer and closer to the wall without ever reaching the wall. So physically, not possible, okay? But mathematically, possible, all right? That's why mathematics is fun. Okay? What do you think we call something on a graph that we get closer and closer and closer to, but we never actually reach it? Huh? An asymptote, just like in our last unit when we were graphing rational functions, and we saw when we got to the horizontal asymptote part, right? We did that like crazy chart where we tried to find where the ends were going. and it so happened that you plugged in stuff, and there was change, and then the change kind of slowed down, and it was changing little teeny bits, but it was just approaching one single number. And that's exactly what's happening here. So what's happening here is there's this asymptote at 0 because your graph gets closer and closer to that but never reaches it. It's horizontal, so it's at y equals 0. And then you have this curve that's growing, and think about your exponent rules if you wanted to get a couple of specific points. When you plug 0 in as an exponent, what do you get as the result no matter what the base is? Like, what is 2 to the power of 0? 1. Or you could look on your table on your calculator. What is 2 to the power of 1? 2. 2 to the power of 2? 4. So there's that doubling, like that jumping that you guys saw on the table. What's 2 to the power of negative 1? 1/2. 2 to the power of negative 2? 1/4. I'm not going to be able to make them look any closer. 1/8, 1/16, etc. Right? So you're getting this curve. It looks like this, where on this end it's growing drastically, and on this other end it's getting closer and closer to becoming 0, okay, but not actually reaching it. Okay? All right, so then I want you guys to take a minute, and I want you now to do the same thing with y equals 5 to the power of x. And what I'm going to ask you in your groups is, how is this graph the same, and how is it different from the graph of y equals 2 to the x? Okay, so we just did 2 to the x together. Right now, do 5 to the x with your group. Look at all the same things we looked at, and be prepared to answer how is it the same as the other graph, and how is it different. Okay, who can tell me how the graphs are the same? Julia? Okay, so they both have a horizontal asymptote at 0, meaning they both have that same pattern of getting closer to 0 without x actually ever crossing it.
And they also, like, if you plug in 0, the x still holds, the y value will still be 1.
Okay, and if you plug in 0 for x, the y value will still be 1. So it still has this point at 0, 1, and this asymptote at y equals 0. So that's what they have in common. Okay. What about the shape of the graph? Is it generally the same shape? Okay, then what is different about these graphs? Allison?
This line where it goes up at a steeper angle by 5 and 2.
Good. So because we're raising 5 to different powers now, it's growing at an even faster rate of 5. In general, it's the same shape, right? It goes from getting close to 0, crossing through this point, and then growing very fast, but growing even faster than the function we saw before, because here if you plug in 1, you get 5. If I can count to 5, there we go. And if we plug in negative 1, we get 1/5. So not only is it growing faster upward, but it's getting closer to the asymptote a little bit faster because of that base of 5. Matt? Perhaps. So did you guys hear what Matt asked? Is this like the graph of a geometric series? Do you guys feel like this is like the graph of a geometric series? Let's think about what the y values would look like if we plugged them in, right? If you made a geometric series where you just raised 5 to the power, then your first term would be 5. If we're thinking of like 1, plugging in 1 as being the first outcome. Okay? Then when you plug in 2, what would you get? 25. When you plug in 3, you would get 125. Okay, when you plug in 4, you would get 625. Okay? So does this follow the rule of a geometric series? Is there a common ratio between all the terms, or a sequence, okay, depending on what you're exactly looking at? But yeah, okay? So interesting connection between something that we were calling a geometric series, just a list of numbers in a pattern, and what that might look like on a graph, and maybe what it could possibly describe. Okay? All right. Next thing I want you guys to look at is the graph of 1/2 to the power of x. So my same questions are going to be asked. You're going to look at the same things. You're going to talk with your group, and we're going to ask, how is this graph the same and how is it different? We're not going to call on the same people. So either new volunteers, and if no one's volunteering, we will pick people. So be prepared. When you plug in 1/2 to the power of x, just a fair warning, sometimes your calculator doesn't know where you're putting the exponent. So anytime you enter a fraction, you might want to enter the fraction altogether and then say to the power of x. It may not matter in this case because 1 raised to any power is still going to be 1 in the numerator. So even if your calculator thought you were just raising 2 to powers, it's not going to look different than if you raised the whole thing. But in the future, if this was something like 2/3, it would matter, and you would do wrong calculations if your calculator didn't know that that entire fraction was being raised to the power. So just kind of an important note about notation. Okay. All right, so things that we noticed. Min Chao. Okay, and what type of reflection would you say? Good. Okay, so the curve before appeared to be towards the asymptote that way, and as we moved across the graph towards the right is when it went up. So if you horizontally reflect that, what you're telling me is that your new graph looks something like this. Okay? All right, so shape-wise it looks like a reflection. What else? Things that are similar, things that are different. So the shape looks like a reflection. What about some key pieces that we had on there before that might be the same or might be different? Bailey? Okay, yeah, so the fact that it's a reflection, it's very interesting that in this case, we actually get bigger when we plug in more negative numbers and smaller when we plug in the larger numbers. Why is that happening? Shannon? Okay, good. So when you're using like 2 to the x or 5 to the x, it's exactly opposite of that. So let's dig even a little bit deeper. Why is it opposite of that? Excuse me, Matt. Okay, so a negative exponent uses the reciprocal. So before, when we had a nice number 2, when we started to attach a negative exponent to it, it got smaller because we were taking the 2 and flipping it over, and it's like we were using 1/2. But now that we're starting with 1/2, if you attach a negative exponent to 1/2, that negative is going to take the reciprocal of 1/2, and it's really going to be like you're using a base of 2. Okay, so that's why the negative powers are getting bigger, because they're raising 2 to a power after they flip it over instead of 1/2 to a power. Okay? All right. So what else? What about some specific points on this graph? What happens here, Julia? Good. So it still has the point 0, 1. Okay. What else? Matt? Good. It still eventually gets closer and closer to becoming, but doesn't actually meet this line at 0. Except for over here, when I plug in positive 1, I get 1/2, and positive 2 is 1/4, and then 1/8. Negative 1 is 2, and negative 2 is 4. So they are different in the pattern of their shape and in the direction that they're going. However, they're similar in the fact that they still have this consistent point and they still approach this same asymptote. Okay? All right, so if we looked at one more, let's talk about what we think is going to happen before we plug it in. What do you think is going to happen if we plug in 2/3? Which shape do you think it's going to be most like? You guys don't know. People are writing stuff down. Okay, then do it. Go through it. Do the same thing as before. With your group, graph it, see what happens when it gets bigger and smaller. Similarities and differences. Right. Okay, good. So it also looks like a horizontal reflection of the original graph we looked at. So again, we feel like the shape is going this direction. Okay. Matt? Okay, and he feels like it's a horizontal stretch. Okay. We'll talk about if it really is. This one's a little bit weird because there's actually a bunch of different parent functions, so we're going to talk about that. Julia. Still has this point at 0, 1. And guess where the asymptote is?
0.
At 0. And then again, it's going this way. So these functions that we're talking about, sorry, Alex, did you have something to add? No, there's not a vertical asymptote, but it's a good question. There's going to be in some graphs that we see later on. There's not a vertical asymptote in this. It might look almost like there is. Why does there almost appear to be a vertical asymptote even though there's not? Cody?
Because each time x increases by 1, the y value increases
Good. Okay, every time we move over 1, we're increasing drastically from where we were before. So to us, it's almost appearing to be vertical. But the reason I know for sure there is no vertical asymptote is because is there a place where I cannot plug in an x value? No. I can plug in whatever I want to the exponent, right? Negative numbers, fractions, radicals. It might be some scary thing I have to go type into a calculator to understand what its value is. But can I plug in anything? Yeah. Okay. So remember, our vertical asymptotes only exist, 1, if our function is literally shooting up towards infinity without ever crossing over another point. And 2, it's there to specifically mark an x value that you cannot plug into the function and get a result. But here, any x value that you challenge to plug in, we can plug in as long as we're using real numbers. Okay, we can plug in and we would be able to calculate an answer. Okay, good question, Alex. All right. So these functions have a special name. Any guess what type of functions these all fall into that we've been looking at? What do we think? Who besides Julia and Lin Chao? They all already talked to me today. What do you think we might call these types of functions? Cody? No. We're going to get to those, though. Addie? No, but that is a good guess because they do have the same properties as geometric sequences. Okay, so that's not a bad idea. Okay, but it has to do with the way you write the rule of the geometric sequence. So a geometric sequence is a list of numbers, and when you write the rule, okay, what mathematical operation do you have to use to write the rule of the geometric sequences? Alex? Good. You have to use an exponent, and notice these are different. So you might be like, we've used exponents before. Why didn't we call those exponential? Because notice what's in the exponent this time. You used exponents before, but usually the exponent was not the place that you plugged in the input. Okay? Like we graphed y equals x to the second power. Yes, we were using an exponent, but the exponent was a very specific number that did not change. In an exponential function, you change the exponent, and it's the base that's staying the same. Okay? Now, exponential functions fall into 2 categories. One category is called growth, and one category is called decay. All right, and these are very closely related to some things you may have studied in science, like population growth, half-life. How many of you guys have heard the term half-life of an object or something like that? Okay, that has to do with exponential functions. All right, so growth and decay, and half-life would be a decaying thing because usually the half-life is telling you how long it takes for half of the object to decay, right? Something like that. Okay, so it's like a decaying function. All right, so which ones do you think are growth and which ones do you think are decay that we looked at? Julia? Okay, so we looked at whole numbers and fractions, okay? So the whole numbers were growth and the fractions were decay. Now, we can't leave that statement just as it is mathematically. That doesn't work, okay? It's not that any fraction is definitely decay and any whole number is definitely growth, okay? It's a little more specific than that. So let me give you an example. I could take this and rewrite this function right here like this. And this would actually be growth and not decay, even though I used a fraction. Okay? Mona?
Oh, I thought you asked me to
Yeah.
Oh, because the denominator has to be greater than the numerator for it to be decay.
Okay, good. The denominator has to be greater than the numerator for it to be decay. In other words, the value of the fraction has to be what for it to be decay? Less than 1. And if it's bigger than 1, then we're looking at growth. Okay? So we want to summarize that right now on our paper. We want to make sure we're familiar with the fact these are called exponential functions, and they fall into these 2 categories of exponential growth versus exponential decay. So growth, like you guys saw, it had that point at 0, 1. It had that asymptote. Decay had those same things. So those are kind of the unchanging things in an exponential function. Now, I do have to warn you that the exponential functions that you looked at, were they probably as complicated as they could be? Well, you can like multiply stuff on the front, you could put more stuff in the exponent, you can add stuff at the end, and then you could change where things are. But if you're looking at just a base with x as the exponent, it will always have the point 0, 1 and this asymptote at 0. And then growth is going to grow away from the asymptote. and decay is going to decay towards the asymptote as you move across the graph. Notice, is either one of these underneath the axis? Okay, because we didn't do any reflections or anything, right? So how could I get this graph to flip below the axis? What kind of transformation would have to happen to make this curve end up, say, down here? What kind of transformation would that be? So our transformations fall into the categories of stretches and compressions, reflections, or translations. In order to get this to become this, what type of transformation would it be? Grant? Good, a vertical reflection. And how would a vertical reflection show up in the equation? A negative. And where would that negative kind of be located? Yeah, like out in front of the power, right? So like maybe something like this, like negative 3 to the x or something like that, okay? This is still growth. It still grows away from the asymptote, right? Just in the other direction, okay? So growth and decay, though you often associate those words with like positivity and negativity, don't have anything to do with positivity and negativity. That's once you started transforming the curve, reflecting it, and things like that, okay? So this curve could also have a reflection. It could end up down here. You guys know like one graph doesn't look like this, right? I'm showing you multiple options, okay? It could also look like this with a vertical reflection. And though the graph seems to be rising, it's still decay because it's still going from far away from the asymptote, decaying towards the asymptote as you move across the graph. So don't let growth and decay in your mind be associated with positive or negative. That's a whole nother transformation. It's just whether as you go across the graph, is it getting closer to the asymptote or getting further away from it? Okay? So both of these equations, so far we just look like having a base to an exponent. Okay? So, yeah, Mincha, sorry. Uh-huh. Say it louder. Uh-huh. Okay, good. If you put the base to a negative x power, will it become a decay? This question is worthy of a new page. Okay, so remember when we first graphed the first couple ones, they looked like this? And then you guys graphed the next ones, and you all said they looked like horizontal reflections of the original ones? Okay? A horizontal reflection is when we use a negative, but we use it kind of within the function, right? Within the exponential function means it would go in the exponent. So think about if you applied this to your function.
Would it flip around, like, vertically, like on the axis?
Well, this would flip it horizontally. So putting a negative in the exponent doesn't flip it from up to down. It flips it from left to right, okay? Or right to left. Okay. Julia? Good. So we normally don't leave things written like this. Now you might see a function like this, but both Min Chao and Julia are right. This basically does become, okay, the decay function we were talking about. This looks like a growth function, okay? And you could say this is a growth function that has been horizontally reflected. But think about if you rewrote this, that's like a 2 with a negative 1 exponent, and then it has an exponent, x exponent on it also, okay? What does this part calculate as? 2 to the power of negative 1. Pardon? 1/2. So that means it really is like 1/2 with just a regular x exponent on it. And how would you describe this function? Decay, right? So really, a growth function with a horizontal reflection will end up being the same thing as a decay function. So yes, Minchao, that's the answer to your question. If you have a horizontal reflection, or you put a negative in the exponent, does it change it from growth to decay? It does, and that connects back to what you guys said when I said, how are the graphs the same and different? The first thing you guys said when it switched the other way was, it looks like a horizontal reflection. It is, but that also means it could be written that way, which is the difference between growth and decay. Okay? So this kind of interesting connection between the way we've seen graphs transformed. If we apply the exponent rule, we can literally see the difference between the growth and the decay function. Okay? All the functions so far, we didn't do anything extra to them, so you have some base to the power of x. Bummer about these functions, okay? The parent function for the square root was always just like the square root of x. The parent function for the quadratic was just x squared every single time you graphed any quadratic. Right? The exponent functions change because there's this new element of what is the base. Okay? If the base changes, your parent function changes. Because if it's 2 to the power of x, that's going to have a different steepness in the curve than if it's 3 to the power of x. So the bummer is you can do all the transformations we've done before, but the parent graph is just a little bit trickier to get at the beginning. You have to actually think about what the base is. You can't just memorize the same 3 points for every exponential function. The points are going to change. Now, you do get 1 point for free. With every exponential function, it's for sure going to have the point 0, 1 in its parent function. Okay? And then we said growth was when the base was bigger than 1, and decay is when the base is less than 1. We're going to put a little clause on here that says it has to be bigger than 0. If we used negative numbers, it would be much different. Does anybody know how the graph would look different if the base had been a negative number? Take out your calculators real quick and graph this function. Make sure the negative is in the parentheses, okay? So graph y equals negative 2. This basically sums up the basics of what the exponential growth and decay function look like. So your homework tonight is going to be to look at video notes that are all about graphing the exponential functions if we start to incorporate all the transformations, okay? So now you learned a new shape. You learned it's a little more complicated than some of the other shapes because the base can change. But you already know the world of transformations that exist. So the graphing notes are going to be how to quickly get these graphs and then transform them and know where those points end up after all of the different reflections and translations and compressions and stretches, okay? Then there's going to be a couple of notes that involve some formula work, a little more algebraic stuff about things in real life that grow exponentially or decay exponentially, like the value of a car. You know how people say, like, oh, you drive that new car off the lot, like it already loses, like, this much of its value. Cars don't tend to decay like linearly in value. It's like as time goes on, they tend to drop drastically. Now, of course, if time really, really goes on, eventually they probably have an upswing. But at the beginning, they tend to follow like an exponential decay type of function. Okay, so we'll look at some different ways we could calculate different values of things increasing and decreasing in value. Alex?
Is it possible for it to do like
It's up here in a second.